Yeah, or go back to the meeting. So as I was explaining, this is our 17th meeting for the SIGCOMM Paper Reading Group. I think it's almost a year. We started the first one in October last year, 2024. So yeah, we're almost 1 year. So the goal for this paper reading group is both educational and research. For the purpose of education, every 2 weeks we invite a student. Uh, Anyone can volunteer, or I'll try to find one who I know to present a paper from SIGCOMM or NSDI or other top conferences. And then, and in the meantime, in the second part of the meeting, we will invite one or two authors of the paper to join the live Q&A and discussion. So today we are honored. Because in 2 weeks we are going to have our SIGCOMM 2025 in Portugal. So for last meeting and this meeting, we will focus on two NSDI 2025 papers to preheat for the new season. So this week we will together try to read a learning production optimize congestion control selection for Alibaba Cloud CDN. So from the title, you already know this paper is about congestion control, a very classic but everlasting topic in networking, and also a global cloud content delivery network. And this paper is a joint work from Alibaba Cloud, Zheng University, and Ennan University. And for presenter, we invited Eric, a research associate from Chinese University of Hong Kong, to make the presentation. Thanks, Eric. And Eric will give a 25 or 30 around about 30-minute presentation of this paper. And after that, we also have the fourth author, Dr. Xuan Zeng, who joined us as a guest of honor for a live Q&A discussion. So I think without further ado, Eric, you can start your presentation. Thank you.
Yeah, thanks for the opening. Hello, everyone. My name is Eric. I'm from the Chinese University of Hong Kong. Today, I'm going to present a work from NSDI 2025, Learning Production Optimized Congestion Control Selection for Alibaba Cloud CDN. So this work is by Alibaba Cloud, Sun Yat-sen University, and Nanjing University. And we are also happy to have the first author, Dr. Xuan Zeng, here today. So if you have any question, feel free to discuss with him afterwards. Okay, so I will start my presentation. So the background of this work begins with short video service on CDN. So content delivery network, CDN carries 70% of global traffic. So it is a significant amount of traffic. Among this traffic, short video is one major workload among all the services. For short videos, we target both high QoE, quality of experience of users, as well as low bandwidth cost, so that the companies can reduce expenses. So here are some characteristics for short videos. So each short video only contributes to a low traffic due to its length. And also for the QoE, we usually refer to like the rebuffer rates other than the bit rate or resolution. There are some existing approaches to deal with it. The first type of approach is application layer strategies. For example, we can have ABR, adaptive.
Yeah. No, you can take it. No, it's not.
So the first type is ABR, adaptive bitrate algorithm. That's to adapt to the network condition. Or we can prefetch short videos to the client side, or we can upgrade to HTTP 2 or 3 to improve the network performance. However, all these methods are implemented at client side, so they are less controllable for the CDN providers. The second type of approach is transport layer strategies. In this case, we adjust a specific type of CC, congestion control here. For example, we can perform parameter tuning of existing CCs, such as using Bayesian optimization. However, in this case, we can't fix inherent design limitations. For example, from the experience of tuning cubic in 4G, more bandwidth is needed to achieve a similar QoE. Or we can also invent new CC by machine learning techniques like offline reinforcement learning. But we will experience inadequate production testing, and we can't provide performance guarantee. Therefore, we need the third type of approach. Because a single CC is insufficient, and the measurement reveals no CC is always optimal. So we need the third type approach, CC selection, CCS. So using CCS provides us full control and feasibility, surpass each CC's limitations, and also it can provide worst case guarantee. Next, there are some motivations in this work. So the author has performed some experiments comparing the existing CC algorithms, cubic and BBR. So they performed alpha beta test for 2 weeks. And in this figure, red means cubic achieves better performance and blue means BBR achieves better performance. So these two figures shows the rebuffer rate and also the bandwidth cost. And from the figures, we can observe that different regions has varying results. There is no standard algorithm that can achieve better performance in all the regions. Since one CC for all yields suboptimal results due to the diversity of CDN environments, there is a question how to apply machine learning to select the best CC for distinct CDN nodes with dynamic environments. To answer this, this work first identified some key challenges in applying machine learning to CCS in production CDN. And after that, they have some design to deal with these challenges. The first challenge is scalability and generalizability. It is impractical to have one model per node due to the scale of CDN networks. And the solution is to train a unified model that's deployed across all CDN nodes. The second challenge is interpretability. From troubleshooting and iterates, due to the incremental developments, requires a clear understanding of the model's behavior. So interpretability is essential. And the third challenge is inference overhead. How to minimize the impacts of model inference delay due to the complexity of deep learning models. So the first design is related to the model design and training method for scalability and generalization. First, there is some observations driving RDCCS model design. The author has performed a feature analysis to identify the top 10 features on the CDN with the highest information gain for predicting the best CC candidates. So from the results, the network type decisively impacts CC's advantages. Why is it? It is because cubic 1CC algorithm struggles in 4G due to rate limiting, and another algorithm, BBR, degrades in Wi-Fi due to frame aggregation in Wi-Fi. Therefore, the network type, 4G or Wi-Fi, will affect the performance of CC algorithms. Also, we noticed that the network types need to be predicted dynamically because the /24 IP prefix shifts dominant network type in 15 hours with 90% of probability. However, reports from clients only accounts for 10% of the requests. It means that only around 10% of those requests carry explicit clients provide labels for the network type, and the remaining 90% doesn't have the explicit label for the network type. An alternative way would be having a private IP database, MaxMind, but it only has a limited coverage and accuracy. So this work proposed to reduce CCS as a supervised classification problem on network type that maps TCP statistics to network types. In terms of the model design, how to learn a generalized model, there exists an issue with the hidden states in the network. For example, using congestion window CWNZ as feature X. For example, if we have two nodes here, one node with a high link capacity, another node with a low link capacity. A high link capacity will lead to a high congestion window, and a low link capacity will lead to a low congestion window. But in this case, there is an inconsistency, and it causes trouble in learning unified model because there is an inconsistent association between the network type, Wi-Fi, and the TCP matrix. So there is a key observation to solve this problem. There exists a one-to-one mapping between the /24 IP prefix and the internet path, so-called the hidden states we care in this case. So we want to find a representation which is invariant to the /24 IP prefix. So it is invariant to the hidden states that we doesn't want to cause trouble. So how can we achieve this? We can decompose the raw data features, which are TCP statistics X, into two parts, denoted by XY and XZ respectively. We create a model based only on features XY for model stability, which is not affected by the hidden states Z. And we construct a decomposed causal graphical model, CGM, and tease apart the impacts of network types Y and hidden states Z on TCP statistics X by leveraging the one-to-one mapping between network paths and IP address prefixes observable on CDN servers. This ensures a stable model that maps X to Y while invariance to the Z, to the hidden state. And we can achieve this by using generative adversarial network, GAN, integrating this decomposed CGM into a GAN. So the next slide shows the overall framework of the GAN-based model to extract features invariance to network hidden states. On the left-hand side, there is a clustering algorithm. This algorithm is used to provide scalability with domain knowledge-assisted clustering. We first separate the training data based on Y, which is the network type, Wi-Fi and 4G. After that, we group the IP/24 prefixes by clustering. By using clustering, we can achieve scalability by distinguish which IP group rather than predicting like the specific IP prefix. Therefore, the searching space is reduced. Then we have the feature generator here. It takes the inputs and provides the output, the transformed feature representation that is invariant to path-specific noise, but it's still informative for predicting the network type, Wi-Fi or 4G. Here, we also have the feature discriminator. There are two discriminators here, each outputting which /24 prefix group the sample comes from. For Wi-Fi, there's Y equals to 1 and 4G, Y equals to 0. And finally, there is a feature classifier. the text that generates output features predicts the network type, Wi-Fi or 4G. The second design is knowledge distillation in decision tree for interpretability. RCCS design is to have a distillation to decision trees. They perform knowledge distillation to convert DNN models to decision trees. After that, we can perform observations using the tree to identify key features for prediction error. For example, they reviewed excessive reliances on MSS feature for specific /16 IP prefix. After this observation, the authors can reduce MSS reliance by using a wider range of features so that the final accuracy can be boosted. So this is the importance of having interpretability in RCCS. And the third design is an optimized inference pipeline for managing inference overhead. This design is based on 2 observations to reduce overhead. So the first observation is a consistent CCS in terms of IP prefix similarity. So the graph shows that CCS stays the same, almost the same under the /24 prefix. And the second observation is the consistent CCS in temporal stability. And /24 IP prefix dominated by either Wi-Fi or 4G for more than 2 hours with 87% of probability indicates that CCS usually stays the same for hours. So based on the previous observations, there is a pipeline that can reduce inference overhead by using IP prefix-based cache to reduce the latency. So there is first an offline processing pipeline. So this offline pipeline will collect and process the logs offline and then periodically updates the results. For the online processing pipeline later on, when there are some new incoming TCP connect requests, we will search for the cache memory. If there is a cache hit, then we can set the CCS immediately. If there is not a cache hit, maybe we can fall back to the default configuration. And there are some evaluation results based on real-world deployments. So this deployments consists of 400 nodes of 3 main ISPs in China, covering almost all provinces in China. So the first result is the rebuffer rate here. So this figure shows the rebuffer rate before and after the deployment of RCCS. From the figure, there is an average rebuffer rate reduction of 4.9%. And for your information, 2 to 3% difference in service quality already matters for market competition. So 4.9% is actually a good number. Another experiment is the retransmission rates reduction. So this figure shows the retransmission rates reduction in different provinces. And the experimental result shows there is an average retransmission rate reduction of 60%. So also a good number. Another evaluation is a trace-driven comparison. So the author compares RCCS with other state-of-the-arts. And from the results, there are low percentile rebuffer rates. There are some low percentile results. From these low percentile results on the left, it shows that RCCS performs similar with other methods. However, in terms of poor condition, early CCS actually performs better compared to other methods, except Oracle, which is the theoretical upper bound. So as you can see, the bars, early CCS has a lower value compared to the other state-of-the-art methods. So early CCS is performing better than them. Also, we compare the implementation efficiency here. So we compared early CCS with non-optimized online inference. And from the results, early CCS has an improvement in terms of processing delay. It has a 64 times better processing delay. And for the maximum query per second, early CCS also has a 2 times improvements. Finally, the author has shared some lessons learned from the experience of over 1 year deployments. First, preventing throughput fluctuations is crucial for CC design of short video services. Rate limiting plays an important role in CC design because maintaining throughput stability is more important than the average throughput for short videos. Second, distributed inference architecture avoids CDN server bottlenecking and is cost-effective by offloading to edge nodes. Third, intelligent CCS exhibits enhanced performance in IPv6 due to stable mapping between IP prefix and the subnets, which helps to improve history-based prediction, which is required by CCS solutions. Conclusion and limitation. Regional and temporal variability in CC advantages necessitates research on intelligent CCS for CDN. Next, distributed inference pipeline can reduce latency in machine learning-based CDN systems with stable input-output patterns. And finally, the formulation of CCS as a machine learning classification task requires pre-deployment tests and domain knowledge. So this is the end of my sharing. Thank you very much.
Okay. Thank you, Eric, for the insightful presentation. And now I'd like to open the floor for questions and comments from the audience. And I see Joseph Chen has put a question in the chat box, and he asked, what analysis did you use to compute the information gain from the different features, such as network type?
Xuan, you might want to unmute yourself first.
Sorry.
And,
So hello, everyone. Maybe let me explain on behalf of all the authors for the questions. So for evaluating the information gain, basically we actually conducted larger scale measurements for about 2 weeks, and basically we collected the rebuffer rates during the two weeks, and basically we group for each network prefix, we basically did a A/B test to compare the winner of the rebuffer rate for both cubic and VBR. So then we can label each IP network prefix with the winner, and after that we can get a labeled data set. Based on that, we basically we can perform the computation of the information gain. Basically, it's like the standard computation for classification problem. So I'm not sure if I explained your questions. So Here,
does that answer your question?
Yeah. So, sorry.
Okay.
Xuan,
Yeah.
yeah, go ahead.
I
Look,
think.
sorry, I
Yeah.
didn't
Okay.
interrupt.
Okay.
Yeah.
Okay. The next question is, why is the CCA performance so regional, which has shown, for instance, in one of the first plots? It makes sense that the network type has a huge impact on CCA performance, but does not depend on region. Also, network conditions change over time, which means the performance of different CCAs changes over time, no? Okay, this is also one question I want to ask. Yeah.
Yeah, I think that's a very good question. So for why the CCS depends on the region. So actually, we have also did some deeper study to understand this phenomenon. If you're interested, I suggest you to check the details in the paper. And basically, the problem that the different region is operated by different operators, and what we observed is that the main operators in China, they have applied very different policy in different provinces. That's why we see very different performance for different CC algorithms even in nearby regions. Yeah. So that's the answer to the first question. And also for the second question, yeah, you are right. Actually, the network is very dynamic. We also observe that even for the network type is changing dynamically over time. But the key reason why we can reliably decide the best congestion control algorithm based on the network type is that what we observe is that the main factor that is affecting the video rebuffer rate is a rate limiting enforced by the ISPs. So and that factor is actually strongly associated with network type. That's why we can focus on network type and reliably predict the best CCS over time. So for more details, I suggest you to check the paper, and we have some explanations and some numbers in the appendix.
Okay. The audience also proposed the question. He asked, Ali CCS looks at IP prefix as input, but the same prefix needn't imply the same network type. So why does this work?
Yeah, good question. So even for the same /24 IP prefix, maybe behind that we have NOTs or some complex networks that may not look the same, may not look uniform under the same /24 IP prefix. But what we observed that it's sufficiently uniform for relatively long time, like for hours, like for 1 or 2 hours, the /24 IP prefix will be statically mapped to the same network. So so this is a lot more like a practical observation. So I think it's because of the network ISP's policy that they don't change the /24 IP prefix that much. So this allows us to use this technique to to resolve the problem of the hidden states. Yeah.
Okay. Okay. I think the audience has no problem. And there is another question. Matthew asked, does the approach introduce any new attack surfaces? For example, could an adversary inject traffic bursts to cause losses or otherwise influence the selection of CCAs?
Yeah, I think that's a very good question. So if you do it on purpose to change some of the distributions of the TCP statistics in order to impact the RDCCS decisions, I think that's possible. But what I can say is that because of the use of this GAN-based model, we are trying to elevate this impact from some extraordinary network conditions. So basically, we are trying to get a unified representation from different network conditions. So in that case, I think even though you can launch an attack to impact one of the /24 IP prefix, but globally, I think when we try to unify the representation, we can reduce the impact of those, and without saying some worst case performances in some of the CDN nodes. Yeah.
Okay, thanks. The next question: would Ali CCS houses fairness issue with regard to other traffic that coexisted in the network?
Yeah, actually, this is a very good question. So we have also considered this problem in the initial phase of the deployment. Actually, what we observed is that at least in the mainland of China, the network, especially for carrying the short video traffic, the bandwidth is quite sufficient. So we don't see that many congestions or competing flows, competing issues for different flows, for flows using different CCS strategies. So actually, we also try to we also did some measurement studies. So when we compared the case where with and without Ali CCS, how the background traffic or the traffic of from other services in Alibaba will behave once we deploy Ali CCS. And actually, we didn't see much difference for the background traffic. So so at least for the network in China, I don't think that's a big problem because of the good network or the rich capacity from the main ISP network.
Yeah, Xuan, sorry. That was my question. So, but I do have a couple of follow-up ones. So, looks like my understanding, my takeaway about RDCCS is by choosing different congestion control algorithms for different flows, you end up increase the quality of experience for short videos. Is that correct?
Yes, right. And also it helps to like reduce the bandwidth cost. Yeah.
Right. But but you also just said that because there is always no, sorry, I take that back. You said that the network bandwidth in China's ISP providers such as China Unicom, China Telecom, and so on is there are very high bandwidth in the network. So by switching or selecting CCAs for these short video flows would not affect other flows. So I mean this is a little strange to me. Are you saying that so I will assume that RDCCS it definitely works, right? But if there is if the bandwidth is abundant in the network, and then why would the congestion control be triggered? And how would that affect the quality of experiences here? So sorry, I'm a little bit confused here.
Yeah, I think very good questions. So here it's also related to one of our key observations. Basically, for short videos, because of its low traffic volume, so basically you can finish the flow in just less than 1 second. So most of the time, it's not the bandwidth or the congestions that is affecting the rebuffer rate or the performance. It's more the other factors such as the rate limiting that can cause the congestion control to go up and down and do some fluctuations. And in that case, even though the average bandwidth, average throughput looks good, you still will encounter some rebuffer events because of this fluctuation of the throughput. So basically, what we observe is that when we dynamically select the CCS, we can optimally reduce such kind of throughput fluctuations. That is how we achieve the better rebuffer rate or retransmission rate.
But yeah, so sorry, I probably hogging the microphone for too long, but I really do want to understand. Are you saying that because we know that taking TCP Reno, a very classic congestion control as an example, right? We start with this slow start, and then if we hit a hit congestion like package drop, we go through AIMD, right? Additive increase and multiplicative deduction, right? Reduction. So the decrease. But are you seeing that? So what's the fundamental reason? Well, suppose I do not use AlibCCS. What's the root cause, or which part would hurt the QE of short videos? Is it because the slow start is too slow, or is it because the multiplicative decrease part is too aggressive? We shouldn't cut it to half. Which part contributes to the most hurt to the QE?
So basically, it's the rare events of the cut of the rare event of the congestion window reduction. So because of the rate limiting applied by the operators, so even though you don't have congestions, suppose you do slow start and you increase and you double the congestion window each time, each RTT. But once you hit the rate limiting window of the ISP, you still got a reduction of the congestion window, and that's where you suddenly see a pause or a stop of the receiving of packets, and that hurts the client side's rebuffer rate performance. So I think that's where it makes the difference. So when you have cubic, it basically aggressively try to probe the bandwidth. So it will try to double. It will try to linearly increase the bandwidth, the congestion window until it hits the rate limit threshold. and then you have to halve the bandwidth, halve the congestion window, and then you see a rebuffer rate. But for BBR, it's different. So BBR is by probing the bandwidth and the RTT, and you get the right congestion window, even though you see a sudden packet loss due to the rate limiting. I think that's why when you use BBR, you will not see this kind of bandwidth fluctuations, and you get a better performance. So basically, in a short summary, it's because of the other factors that can also affect the congestion control in the network, like the mobile loss or the rate limiting that makes a difference for different congestion control, especially for short video traffic. That's what we observe. Yeah.
I see. So suppose everyone is using Ali CCS. Suppose in that case, what would happen?
You mean you are talking about the fairness of the clients, or?
Yeah, so sort of, yeah, I think basically not just about fairness. Basically, congestion control is essentially like a very distributed system, right? So every flow would have would employ certain congestion control algorithm, right? And suppose now everyone is using Ali CCS. So I don't know if you have whether you have conduct that sort of experiment in your controlled environment. Like you can have all kinds of flow. You have short video, you have live video, you have a file transfer, you have even machine learning inference workload, all sorts of workflow, and every flow essentially adopts Ali CCS. What would happen? Like what sort of what kind of equilibrium the system would end up in?
I see your point. So I think the key problem is that the CCS itself is somehow also changing the environment. So that will in return also affects your CCS decisions. So I guess once we apply CCS in a global scale and also in all sorts of traffic that is generated by Alibaba Cloud, I guess we have so all those factors such as competing flows and congestions. I think that will play a more important role. So in that case, I don't think our model based on strong association between network type and CCS will be sufficient. In that case, I guess we have to more dynamically update our model to reflect the changes in the network environment. So I guess in that case, we have to use some more like online learning to dynamically adapt our model to this competing and changing network conditions.
I see. So yeah, the reason I'm asking this is because Ali CCS reminds me of a paper called Aurora. I think it was a reinforcement learning based congestion control. But the paper was published in SML, I think in 2019. Yeah, I think that's the correct year. So essentially that paper, I think there are also a bunch of follow-up papers for the designing agents that adopt reinforcement learning to perform congestion control for the flow it works for. Right, so I think that would, of course, I don't remember all the details of the paper, but look, I think essentially the result looks like they indeed they evaluated the fairness and the throughput and the distribution of throughput for different agents for different flows, and the performance looks fairly promising. So, but I'm just wondering, in your case, before you design RDCCS, have you tried to use such learning-based congestion control algorithms? Have you tried that before? How did it work?
Actually, we before launching RDCCS, we have also tried some machine learning to basically invent some new CC algorithms. Like the work from Sarge, and so the one published in 2024 SIGCOMM, and also some other reinforced learning based CC algorithms published in SIGCOMM. But what we observed is that basically when we try to scale up, try to extend the scale of this of the deployment of such algorithm, we don't see the worst case performance guarantees. So it shows some promising results, and you see the performance gains in some of the network conditions. But if you consider the global scale, like trying to test it in more regions in China, you immediately see some very bad worst case performances. That's one of the reasons we didn't choose the path to apply reinforcement learning to invent a new CC to improve the short video services. And another reason comes from the difficulty of CDN itself. So as a CDN provider, we cannot access the clear signal from the client side. Like we cannot get real-time feedback on the video rebuffer rate or some detailed logging information from the client side in order to adapt to such events. And so this comes from the collaboration between the CDN provider and also the source, as well as the service provider, because the client side performance is more like a business secrets from the service providers. They will not easily share this information with us in order to improve their service quality. So in that case, we also have to develop something like a proxy model for modeling their client side performance, and that also creates one of the obstacles preventing us from applying reinforcement learning to improve the short video services. So yeah, I think it's more collaboration problem. So yeah,
I see. But wouldn't that, sorry, there's one point actually that's very related to my next question. So I do have quite a few questions here, but you mentioned that as a CDN provider, there are a lot of information that you couldn't easily get, for example, from the client side or from the provider side, right? But I think Ali Cloud is also a cloud provider, right? So not just a CDN, you are not encountering this challenge in CDN, right? You're also in your cloud service, even your large language model serving services, in all your services, you will encounter similar issues, right? So why did you pick CDN in this paper? Or in other words, would RDCCS work for Ali Cloud's other services to improve the QoE or QoS?
So for the reason why we choose short video services basically is as introduced by Eric. So it's basically the dominant workload on Alibaba Cloud CDN. So it's like I mean all the I think 80% or 90% of the profits basically come from the short video services, and so in order to basically get some profits and to really reduce the cost, we have to focus on the short video services. If we decide to optimize for CDN itself. Also, I think it's also a collaboration problem. Like I understand the question from Professor Xiao, like so basically we have so from our team we have also published other paper like the short video services on the Taobao applications. So in that case, we don't just focus on CDN. We have all the information from both the client side and the server side. So I think it's just the issue of the big company. Like sometimes you get the connections and you can establish a good collaboration and you get those information and you can do whatever you want. But sometimes you just, for some reason, you just cannot break the wall and get those information. So you have to take whatever you can get access to optimize for the network.
I see. Yeah, that makes sense. That makes sense. I think. Yeah, very interesting. Yeah. So sorry, I have been asking too many questions. I think we should give the opportunity to other audience here.
Okay, thanks for your presentation. Okay, so let me I will give the chance to the Chen, and let me rephrase his question. And the question is about, thank you for the insightful talk. I have a question about the design choice in RDCCS. Specifically, if the user are able to directly provide the network type, RDCN can make an immediate decision, but in more realistic cases, where the network type is unknown and RDCCS must infer it. And the question is about how large is the performance gap between these two scenarios. And the next question is about how does this affect the overall system efficiency?
So basically, I think the audience is more curious about why we have to infer this network type instead of leveraging information just from the client side. So basically, the problem that initially we have tried this approach, like we try to ask the service provider to provide such network information so that we can immediately get this performance gain by applying our CCS strategies. So the problem that in the end we found that what we found is that first of all this information is not fully available. Like only 10% of the client requests can PG back such information for us. This is more due to some software issues. Like you can never ask all the clients to upgrade their software to support some features. So so this is a big overhead, and the service provider will not pay such cost just to help us to improve their performance. And secondly, even though even if the service provider are willing to collaborate, and what we observe is that sometimes so even on the client side, they cannot reliably decide their network type. So actually, we compare the predictions from our model and also the with that from the with that from the client side. And what we found that is that sometimes the client just will misleadingly report their network type because of I guess the software issues like the Android or iOS. Sometimes they just cannot reliably decide what is their network type. So this information is not that reliable. So what we found is that actually I can share an experience that actually we have compared the two cases. Like the first one, we just use the information piggyback from the client side, and we apply AliCTNs. And the second one is we don't trust the client. We try to infer the network type using our model, and we make the decision based on our model's inference results. What we found is that by applying the machine learning model, actually we achieve a better performance than the one using only the information from the client side. So I guess because we are leveraging information from multiple dimensions like congestion window or RTT and many other TCD statistics. So we end up with a more reliable predictions for the network type and get a better results. So I don't know if that case explains your question.
Okay, we have one more question from Haoran, and he asks about could you go more abstract than network type and make a CCA choice based on the distribution of package losses and bandwidth fluctuations?
Yeah. That is I think this is a very good question. So actually we in the early phase we also tried this approach. So basically if we have enough data for labeling the winner of the CCS, right? So we have, like, for example, as the audience suggested, we have for each request, we have a label for which CC algorithm is better, and we get the TCP statistics like the packet loss and bandwidth fluctuations. Then we can train a classification model and apply that to directly obtain the CCS result, right? So that could be more efficient. So actually, we are also working on that. But the key issue is that for labeling the winner, we have less data support to train such models. So for the collaboration with the service providers, they are more willing to provide information such as the network type or some other network information from the client side, but they are not willing to directly reporting their rebuffer rates or some more critical service quality metrics, because I guess this is because this is more their business secrets. So in that case, so if we decide to train end-to-end model directly to predict the CCS, we will end up with issues in data shortage. So we will have just a very little data from the service provider side, because they are trying to I don't know how to say it. They're trying to hide their real states. So, but they are more willing to provide information on the network type. So we get a rich set of data sets in order to train such models. So yeah, that's the key reason, actually.
Okay, I think there are no more questions, and the time is going to the end. And so today is it's our honor to have the Dr. Xuan, Dr. Xuan here to answer, to introduce their detailed works and give some many different ideas and detailed introduction of the questions from the audience. And let me thank again for the presenter, Eric, and also the author Xuan for his good work in today's hours reading group. And I think time is it. Maybe we can stop here.
Yeah, just a quick notice. So in 2 weeks we were going to have SIGCOMM 2024 in Portugal. So I hope to see maybe not all of you, but some of you in Coimbra, Portugal. Because we will be at SIGCOMM week during that time, so we will suspend one we will hold our meeting on September the 10th, and we will resume the meeting on September 24th, because the week I think the week after the SIGCOMM week would be the NSDI fall deadline, submission deadline. So we will give people to work on that, and after people submit their papers, we will resume our meetings on September 24th. Okay, thank you so much for everyone for listening, and all great discussion, wonderful question, wonderful presentation, wonderful discussion. All right, thank you so much, and we hope to see you in 4 weeks. Thank you. Bye.